Photographers frequently refer to something called color temperature. Color temperature is saying something about the spectrum of the light that they're looking at in terms of the equivalent blackbody radiator. So the spectrum associated with this red sunset is equivalent to a blackbody radiator of about 2000 to 3000 degrees Kelvin. It's a very reddish light. A tungsten light is equivalent to a color temperature of around about 3000 Kelvin. The spectrum of the sun at midday is equivalent to a blackbody radiator of around 5000 to 5400 Kelvin. A photographer would say that the sunlight is bluer than the tungsten light, or they would say that the tungsten light is more red than the midday sun. In the case of an overcast day, the color temperature is in fact even higher. Point in the world is no longer illuminated by the white light from the sun, it's illuminated by the blue light from the sky. And this excess amount of blue in the light is equivalent to a much hotter blackbody radiator. So a photographer would refer to this as a color temperature in the range 8000 to 10,000 Kelvin. Our sun is a very hot object in space and functions as a blackbody radiator. But by the time the light from the sun finds its way down to ground level, the spectrum has been dramatically altered. And that's because of a number of chemicals in the atmosphere. We have ozone, oxygen, water, carbon dioxide, and so on. And each of them remove parts of the radiation that comes from the sun. So by the time the light gets to the ground, the spectrum is a little bit different from an ideal blackbody radiator. The peak of the spectrum of the light by the time it reaches the ground is around about 550 nanometers. It's a middle green color, and not surprisingly, that's the color that our eyes are most sensitive to. A lot of the energy that comes from a blackbody radiator is emitted in parts of the spectrum that we cannot see in these longer wavelengths. And this is one of the reasons that these tungsten light bulbs are being phased out. They convert some of the electrical energy into light that we can see, but they convert an awful lot of it into heat, which doesn't help us see. They're not particularly efficient. So there's a lot of energy being emitted at these longer wavelengths. So if we look at the spectrum here, we can see that the visible part of the spectrum, that region between 400 and 700 nanometers, is actually a very small part of the overall electromagnetic spectrum. With our eyes, we're able to sense electromagnetic radiation in this very narrow part of the overall spectrum. Although we can't see infrared radiation, we can still sense it, and we can feel it as heat, as warmth on our skin. Infrared radiation was discovered by William Herschel, a German-born English astronomer, back in the 1700s. He built an enormous telescope and discovered many stars and planets. And one day he took the light from his telescope, passed it through a prism onto a table, and he put a thermometer into different parts of the spectrum on the table. He was trying to measure the temperature of blue and yellow and violet and red. And what surprised him was that when he put the thermometer into an area of the table where he couldn't see any light, the thermometer still recorded a high temperature. So there was radiation that was heating the thermometer, but he was unable to see it. So he discovered infrared radiation, and he referred to them as calorific rays. I mentioned before that we can sense infrared radiation as heat. There are devices called thermal cameras, and they're very sensitive to this infrared radiation in what's called the thermal or long infrared band between 9 and 14 micrometers. That's 9,000 to 14,000 nanometers, the units that we're using previously. And in that part of the spectrum, human beings emit energy. And so you can see that people here are warm against a colder background. This is our natural body temperature, 37 degrees Celsius. It means we ourselves are blackbody radiators. We're emitting not much, but a small amount of infrared energy, and a thermal camera can pick this up. Thermal cameras are often used to diagnose heat loss from buildings. The outside of a building should be cool, but if there are hot spots, it generally tends to indicate that heat is leaking from inside the building to the outside world. The fire beetle is exquisitely sensitive to infrared radiation. It likes to lay its eggs into burnt trees. So it goes hunting for forest fires, and to do that, it uses special infrared sensing organs built into its thorax. There are also a large number of non-blackbody illuminants. Light-emitting diodes, for instance, have got a spectral characteristic like this, quite differently shaped to the blackbody emission spectrum. So here we can see the emission of a blue LED, a green LED, and a red LED. We see that the energy is concentrated into a fairly narrow spectral band. There's no wasted emission in the infrared part of the spectrum, for instance. A compact fluorescent tube has got a very complex spectrum. The light is a mixture of the light emitted by a large number of different phosphors, the white layer inside the helical tube, which is excited by the gas discharge. So each phosphor emits light at a different wavelength. The overall combination of these different wavelengths appears to our eye to be white. Another non-blackbody illuminant is the laser. The laser is perhaps somewhat similar to the light-emitting diode that we looked at a moment ago, except that the spectrum is extremely narrow. Finally, these are the spectral emissions associated with the red, green, and blue phosphors in an old-fashioned cathode ray tube. And this shows the emission spectrum of the blue phosphor, this curve here, the green phosphor, this curve here, and the red phosphor, which contains a large number of quite narrow band emissions, but together, collectively, they appear to the human eye as red. As I mentioned a moment ago, the light that reaches the surface of the planet is partly absorbed by various molecules in the atmosphere of the planet. Water, in particular, is a very strong absorber of light. This graph shows the amount of absorption of light as a function of wavelength. And we can see that there is a region of the spectrum where there is minimal light absorption. If we look just at the visible band and then mark blue and red, we can see that red light is absorbed more than blue light. And this explains why when you're underwater and the further you go underwater, the light has got much more of a blue tint to it. You tend to lose colors like red and green. They tend to disappear and everything starts to look blue, because only the blue light is able to penetrate through a big column of water. So let's summarize. We have light comes from an illuminant, and it produces illuminance of the scene, and we can describe that light in terms of its spectrum. So we use the symbol E to represent the illuminance, and it is a function of the wavelength. And we've looked at various sorts of illuminants. We've looked at blackbody radiators, light-emitting diodes, compact fluorescent tubes, and lasers. Each of them have got a different spectral characteristic.